so we'll start the lecture today. So this is our third lecture, and to recap what we have done in the last class, we looked at the stress tensor and defined the isotropic component as well, right. So we defined the total stress tensor, the isotropic pressure component and the extra stress tensor. We showed that it must be symmetric due to conservation of angular momentum. We simply have defined the normal stress differences. Their relevance we will see in future classes. We have also defined the deformation gradient tensor. We are yet to look at the finger tensor systematically, which we will do in this class. And we will look at examples of uniaxial extension. We did that in part, but we will also be looking at simple shear and rotation. And of course, yesterday we looked at index notation. So those of you who were not there, you all can either borrow notes from your colleagues, or there are two places where you can find index notations. One is the book by Bird, Stewart and Lightfoot as the gradient of x, gradient with a dash because the gradient operator is being applied previous time, and we are taking a transpose of this. So here we would have dou by dou x dash of x, right, and if we have EI and EJ here, then these two are going to get reversed. So this would be EJ and this would be EI. That is where the transpose is getting implemented, right. And so therefore, when we write it in matrix notations, the rows are denoting the numerator quantity and the columns are denoting the derivative quantity, right. And also when we implement a dot product, so for example, when we want to write dx, you will get a certain r, right. And what you will find is that when you rotate it by the angle minus theta, you will get transpose of r, okay. So what that is saying, you rotated, you got r, rotated back, you got r transpose. What is the result? The same thing, rotated and rotated back, and therefore you are getting the identity tensor back, right. Now knowing that r dot r transpose is just I, you can then say that f dot f transpose would be just v dot v transpose, yeah. Or effectively we've found a way of not counting the rotation part by taking f dot f transpose. Now this becomes a quantity of interest because here this only takes deformation into account, and we define this as the finger tensor, finger being the last name of the scientist who defined this, okay. One could start defining constitutive equations with B as well, but often what is done is that we subtract from B the identity tensor, which would have been the same case, right, and get just the strain tensor, or which is also denoted as E. Yeah. So take an example. For the uniaxial extension case, you remember the picture, we had a cubic slab which we had extended in one direction. We had obtained f as a diagonal matrix alpha 1 negative square root alpha 1 negative square root alpha 1 as the diagonal components, and so the tensor B is nothing but square of the it will just have the square of those individual diagonal components there. It is a simple case. Right. So, that is our tensor B, and once we subtract the identity tensor from it, just like if you remember with the total stress tensor we remove the hydrostatic part. Right. So, similarly here we are removing the identity tensor part and you are getting the strain tensor, which is subtracted 1 from all of the diagonal components. Right. So, this was F dot F transpose is going to be B. What is F dot F transpose? In this case, since these are just diagonal tensors, right, the only elements that are going to survive are the multiplication of the diagonal components with themselves. Right. So, alpha 1 times alpha 1 you will get here, alpha 1 to the power minus half multiplied by alpha 1 to the power minus half, you will get alpha 1 to the power minus 1 and so here. Right. So, this we can obtain. In general, if you wanted to write it using index notations, because we are doing F dot F transpose, the index notation form of the finger tensor would be this. So, each IN component, right, could be written as the respective products of the Ij component with the Nj component. So, you see here the indices are switched. Why? Because we are doing F dot F transpose. So, in any general case you could expand this and get the finger tensor from the deformation gradient tensor. And E of course is just B minus the identity matrix, which is straightforward. So, homeworks for you would be to derive these quantities F, B and E for the simple shear case, right, so where you have a slab which is getting deformed to the right here, where the top surface moves to the right by a distance s. So, we can define a quantity gamma which is S by delta x2, and so what you need to do is find out expressions for x1, x2, x3 as a function of the previous state, that is x1 dash, x2 dash, x3 dash, obtain F and then B and then E, and the same case for rotation. Yeah. So, here you have a slab which is getting rotated anticlockwise around axis 3, right, it is going to the left here. So, I should add an arrow, yeah. And so, what would be F for this and what would be B and what would be E? Yeah. Once you do this for theta, you can also do it for minus theta and then convince yourselves that indeed for pure rotation theta and minus theta would be such that when you do one operation after the other, you will just get the identity tensor. Okay. So, a little bit to understand the significance of this finger tensor, right. I do not expect you to be able to do this kind of a derivation on the fly, but it is good to understand that one can derive a physical significance from the finger tensor, which we will be using to in our models going forward, right. So, if you see here, it is a busy slide, but let us take it one thing at a time. This is the picture we have been working from. This is the previous time dx dash, new time, present time t dx, right. We had the previous vector pq which is deformed to the new vector pq, right. Now, what we want to show here is that the finger tensor B represents nothing but a relative change in the local area. Why change in area? Now, if you remember when we did the uniaxial extension, you were pulling in one direction, but there was a change in area in the normal direction, right. So, similarly here this thing is being pulled in some random fashion, but then there is a change in this cross sectional area. Right. So, we will use the volumes to get there. The differential volume here can be thought of as the area vector dA dash dotted with the length dx dash. The area vector is nothing but the magnitude of the area with the direction of the normal, and to get the volume you will dot it with the dx, the direction in which you are sweeping it. Same here, the differential volume would be dA dot dx. Right. Now, conservation of mass requires that rho dot dV dash, rho dash dV dash should be equal to rho dV, right. And so, you can substitute for the volumes here, right. Rho dash dA dash dx dash should be equal to rho dA dx, and rearrange it. You can get an expression for dA dash as rho by rho dash dA dot f, just a rearrangement of this equation. Right away you can say if density is constant you can start ignoring it, right. I have ignored it as a later step. So,
is it okay to take the dx prime from left to right? It's a dot product.
right. So, it is actually df, if you look at the definition of df and you work it backwards you will get that only, right, because f is a gradient. When you dot it with a portion in the denominator you are going to recover that. Just like when we defined x, when we defined f, out here, right. We defined it like this and we can recover dx as f dot dx dash. It is the same operation there, right. Because these are infinitely small elements, right. That is why we are able to do this. Alright, so we are back here. We had reached up to this point dA dash here, and now we want to define the relative change in local area, and so we want the magnitudes of the area. To get a magnitude of the vector you dot it with itself. So, these would be the square of the magnitudes dA dash dot dA dash dA dot dA. We are taking a ratio of these two, that would give us a relative change, and so this is the expression that you will get, right. Now, if you see dA dash dotted with dA dash is going to, these are just scalars, you take them out. So, you get rho by rho dash square, and if you assume density is constant this is gone. Then you have dA dot f dotted with dA dot f. Yeah. And in the denominator you just have dA dot dA. Yeah. You can further show that here you can invert this by taking the transpose, that dA dot f would be same as f transpose dot dA, and you will get this expression, right. Now, f dot f transpose is nothing but our finger tensor, right. So, in a sense dA by dA is just the unit vector in the direction of the area normal to that plane. So, n dot b dot n is nothing but ratio of the squares of the areas, the past area divided by the present area, right. And so, it tells you about the significance of the components of the B tensor, and of course, it has to depend on the particular area orientation you are taking, because not all areas will deform equivalently. So, the operation of n dot b dot n is going to tell you what will be the particular change in the area for that plane. Yeah. Okay. So, so that was about the finger tensor. Now, just to recall, we have already defined the stress tensor. Now, one thing I forgot when incorporating these slides is that in the previous class when we defined the stress tensor, we were using the symbol sigma for the stress tensor, but somehow in these notes I have taken capital T as the stress tensor. So, it is the same thing, but just make a note of that. So, various books land up using different notations. These particular notes were taken from Mikosko, and he has been using capital T as the total stress tensor, right. But the rest of the things are the same. Right. So, we will sometimes have used sigma and sometimes we have used capital T for the total stress tensor. Okay. So, then comes the part where we want to extend the simple Hooke's law, which was for 1D case, to the 3-dimensional case. And the simplest way of doing that is to retain the simplicity of the Hooke's law and consider that we have two tensors, a tensor that describes stress and a tensor that describes the deformation, which is the finger tensor or the strain tensor. And we say that the law or the relation that combines these two is that of proportionality. And so, the stress tensor is proportional to our strain tensor and the proportionality constant is a modulus, right. So, that is the very basic simplest way of putting forward the Hooke's law, right. So, that is what we have there. This is known as the neo-Hookean solid, right. The only difference is that we are looking at the 3-dimensional picture, right, but the thought of the Hooke's law still persists. When making this statement, we made lots of assumptions. One of them is that the material is isotropic, right. So, G is not a function of direction. There are many other assumptions that have gone in, that stress tensor is symmetric, right. We have also included the fact that the system is frame indifferent because rotation has been taken out, right. Had we not taken all of these into picture, the most general equation for that would have been that tau is equal to a tensor G applying some operation on tensor E, right. So, now the most general form of this G would actually have been a 4th order tensor. So, this would have been 4th order tensor G double dotted with the tensor E. That would have been the most general scenario. So, the extent of simplification we have done is telling you that how many terms we have actually thrown out, right. So, what we are looking at is a much more simplified version. Of course, a lot of these terms go out because of the assumptions of isotropic nature, symmetricity and so on, right. Okay. And of course, we are taking tau here and not the total stress tensor because we do not need to include the sort of the isotropic pressure component when doing this, because this is only taking into account the deformation part. Yeah. So, if you wanted to write the total stress tensor, it would be just minus Pi plus G times E. Right. Some notations in some textbooks, they also use B instead of E, and as you will see in some problems, it does not really matter what you take because the isotropic part actually cancels out, but just alerting you to this. We would be using this convention. Right. So, now you know how to define the stress tensor for a neo-Hookean solid, and then the question is, would we be able to reproduce this? You remember this chart from an earlier class. we had the stress component T11 given as a function of the elongation ratio, and we discussed that the Hooke's law remains valid for a very small portion close to alpha equal to 1, right. So, you more or less have almost solved it. What remains is the question of P. Right. So, now how do we determine what P is, or how do we eliminate P from this expression? Because ultimately we want to plot T11 versus alpha 1, right. We cannot do that unless we know what P is. G of course is a proportionality constant. What do we do with P here? No, I mean they are there. We are definitely interested in them. We would like to define the entire system. But can we use them? Sorry, please say that again.
If you are only interested in one of the just like T tau alpha, then the remaining either of it take that as 0 and sign.
So, are you saying that we should put T22 or T33 equal to 0? Okay. And what would that tell us? In terms of G and alpha, P in terms of G and alpha. Okay. But why should we put it equal to 0? That's correct. We could, that's what we are going to do. But then why should we put it equal to 0? Yeah, tell me. Right. So, I think what you are trying to say here is that when we take this object and we are applying a force in one direction, we are not really applying a force in 2 or 3 directions, right. So, they are free surfaces per se, right. So, whatever is the stress, the extra stress that is generated due to deformation, it must balance against P to give us a 0 stress, 0 net stress at the surface, because you know that the force applied is 0, we have not applied any force on it, right. So, by putting T22 and T33 equal to 0, what you can do is you can derive a relationship for P in terms of G and alpha 1, right. And you are able to do that because they are free surfaces. You have not applied a force on the second direction, you have not applied a force on the third direction, which is free. Yes. All right. So, if we do that, we get the expression for P, which can be substituted back in T11, and then you get an overall expression for F, which says that F by A is equal to G, you can just rearrange this, is G alpha 1 square minus 1 by alpha 1. I don't know why I have written this. All right. Yeah. Okay. So, so we go back and that line The neo-Hookean line is actually this expression that we have derived. And you can see that more or less up to alpha of about 5.5 to 6, it does a pretty good job of the experimental data which is there. Beyond that, maybe some non-linearities in the elasticity, in the elastic behavior would be coming up. Right? And so, while it does well for this rubber sample, in general for cross-linked materials, this would do quite well. Right? Rubber being an example of a cross-linked material. Okay. Now, a quick recap to what we generally use to study extension is the strain and not the elongation ratio like alpha we have taken. Right? And an elongation ratio by definition is nothing but strain plus 1. Right? Alpha, which is the new length by old length, can simply be written as 1 plus change in length by old length, which is just 1 plus epsilon. Right? And if you make that substitution, replace alpha 1 by 1 plus epsilon, you will get this expression where T11 is equal to G bracket 1 plus epsilon square minus 1 1 by epsilon. And we are used to seeing relationships which are linear in epsilon. Like when we define the Young's modulus, you know, it's the extensional stress divided by the extensional strain. Right? So, to do that, to linearize this expression, we will take the limit of epsilon tending to 0, and in the limit of epsilon tending to 0, if we expand this expression, the first term is just 1 plus epsilon square, you will get 1 plus 2 epsilon plus an epsilon square term. We will neglect the epsilon square terms for now. And in the second term, you have 1 by 1 plus epsilon. If you Taylor expand it for small epsilon, you will get 1 minus epsilon plus order epsilon square term. You take that, you know, ignore the epsilon square terms and higher, and you will simply get a relationship that T11 is equal to 3G times epsilon. And we know that normally you would have used an expression of this form, E, which is our Young's modulus, is basically sigma 11 minus sigma 22 divided by epsilon in the limit that epsilon tends to 0. Now, sigma 11 minus sigma 22 is something that we have actually already implemented by eliminating pressure from the equation. So, it's an equivalent expression, and what we are getting here is that the Young's modulus is nothing but 3 times G. Right? So, what was an extensional modulus can be shown to be 3 times the shear modulus. So, the symbol G that we have used as a proportionality constant is known as the shear modulus, and this here is the Young's modulus. And such relationships are quite useful because there are scenarios where you have a material, you are interested in the extensional quantity, but maybe the experiment setup that you have only allows you to measure the shear quantity maybe, right. So, if you measure G, then you can postulate that the extensional modulus would be 3 times that. It is the same order of magnitude. If one is 100 Pascal, the other would be 300 Pascal. If G is 100, then that would be 300 Pascal. Yeah, they are different. So, that E is the tensor and this is the modulus. I am using E because the Young's modulus is often denoted as E, but they are two different things. Yes, thanks for pointing this out. This E is not the same as the strain tensor E.
Well, sigma 11 is basically the, in this notation T11.
Yeah, T11. Yeah, apologies. I should have standardized all the slides. T11 and sigma 11 are getting written all over the place. Now, in deriving this, we have used the assumptions of the material being incompressible and isotropic. If you were to remove the incompressibility requirement, then you would add the Poisson's ratio into the picture, right? And we won't derive it now, but if we were to do that, then the expression that you would get is that the Young's modulus is 2g times the Poisson's ratio plus 1. So, for an incompressible material, the Poisson's ratio is 0.5. So, you can see if you substitute 0.5 here, 0.5 plus 1, 1.5 times 2 will give you 3. So, when we study elasticity and solid mechanics, we typically come from this direction. We'll convert somewhere on the way.
Right there, is that the definition of Young's modulus?
Yeah, you can take it as a definition of the Young's modulus. But see again your it's a difference in the normal stresses that are appearing, because we'll end up eliminating P, which is the isotropic component, from the equation, right. So, again why normal stress differences have to be defined, it slowly becomes apparent as we do these derivations, right. So, if you remember, the normal stress differences were sigma 11 minus sigma 22 or sigma 22 minus sigma 33. Right. So, just to give you an example, for Srinidhi's work, actually the student before you, we were, so she works on how stem cells respond to gradients in of rheological properties on the gel substrate, and by creating a gradient on the gel substrate, there is no way of measuring that gradient in a traditional rheometer, right, because you will have to put the entire sample in. So, to measure the gradient, what we had to do was we had to use an AFM, where every portion of the gel was probed with by pressing on it, and the deformation in response to the force tells us what is the local modulus, right. And because we are deforming it normally, it's an extensional kind of a deformation or a compression kind of a deformation. So, we are measuring a quantity which is similar to E, but experimentally when we are creating these gels of uniform composition, we can only get the shear modulus, which is G, right. So, to correlate the two, we resorted to using this kind of a relationship, right. So, if you were to design materials and do experiments, there will be a lot of scenarios where you would want to incorporate this kind of understanding. Yeah. Okay. So, all right. It's useful to talk about what are the typical order of magnitudes of moduli. Are you able to see the slide? Are you able to see the numbers? Yeah. So, you can go from something almost 0, which would be like a liquid, right, and upwards in the strength of the material. So, the highest ones here are diamond, which is about 10 to the power 12 Pascal. So, this is a logarithmic scale, right, every point is a factor of 10 here. So, you have steel and other metals and alloys here. Silk and wood are out here about 10 to the power 10 Pascal, 10 gigapascal. A lot of polymers would fall in the range of gigapascals as well. So, thermosets are here about 1 gigapascal, Foams would be a little softer, they are here. Our natural rubber comes here. Biological system, skin, cartilage and all, you are here at about 10 to the power 5 Pascal. Yeah, that's us here. And muscle, tissue, relatively softer. Yeah. And so if you see, you have this entire range, and what you have done here is you have sort of figured out a relationship that could explain all of these, at least in the small limit of linearity, right. So the applicability of what Hooke's surmised from his initial experiments becomes apparent here also in the wide range of materials that you can apply that relationship to, right. And if you wanted to concentrate only on biological systems, then an expanded version of that is here, where you could go from brain tissue, which is the softest, to bone, which would be one of the hardest in for our biological systems. So about 1 kilopascal or little smaller is where all of our soft matter materials would also fall in, where interactions are of the order of thermal energy, which is kT. We were here. Just like we derived for the uniaxial case, I would like you to, it will be another homework assignment, you will do derivation for the simple shear case using the neo-Hookean model. And hopefully what you will be able to show is that the components of the total stress tensor, the 2-1 component, which would be the shear component, will be proportional to the strain, and you will also be able to show that sigma 1,1 minus sigma 2,2 gives you that quadratic curve, right. So these are experimental data, and you should be able to show that the neo-Hookean model matches this. And this is data for silicone rubber, if I am not mistaken. Okay. So we have discussed simple solids, relatively simple solids. We will look at simple liquids behavior, and then go on to viscoelasticity in the next class, hopefully, right. So when we are talking of liquids, we are talking about flow, and flow will always involve a velocity field associated with it, right. So a velocity field would be the velocity vector v specified at every point r in the system, right. And so just like we derived the deformation gradient tensor, we need to quantify the gradients in velocity in this case. If the entire system is moving at a constant velocity, then there is no internal resistance to that, right. So if this bottle here, if I just translate this bottle, of course every point of this fluid, its average velocity is going to be just forward, right, and there is no internal resistance to that motion, right. So it is only when there is some gradient or some pockets of fluid are moving in one direction, another pocket is moving in another direction, or they are moving with unequal magnitudes of velocities, is where the viscous forces would come in, right. So and of course this understanding could be attributed to Newton, right. Okay. So yeah, so we will go back to this whole past and present thing, right. So past occurring at time t dash, the present is at time t. When we were looking at deformation, it did not matter in how much time we did that, right. But here we are interested in that, because we also want to know how quickly the velocity is changing, or how quickly the displacements are changing, which are going to give us velocities, right. So the previous vector p dash q dash is getting changed to the new vector p q. These are very, very close to each other. So the dx dash and the dx are still infinitely small vectors, and in going from time t dash to t, in this time t minus t dash, when these displacements have occurred, there is also a velocity associated with it, right. So, the displacement from P dash to P occurred with a velocity v, and the displacement from Q dash to Q occurred with a velocity v plus dv, right. And so, the difference in those velocities dv is what we are interested in. And that difference in velocity occurs over a distance dx, and that allows us to define what we have already seen, the velocity gradient tensor, right. So, dv the change in velocity can be written as dou v dou x dotted with dx, right. And we define this part as L, which is our velocity gradient tensor. Yeah. Now again remember, because I am dotting dx from this side, I am actually taking a transpose of this. Just like we defined f as the transpose of that gradient, similarly here we are defining L as the transpose of the velocity gradient vector, right. And so, we could write using index notation that Lij is dou Vi dou xj, xi xj. Again here the first index xi is actually the numerator, just like we had with the deformation gradient tensor, and the second index is the derivative quantity, which is xj, right. And therefore, I can write that L is transpose of grad V, or grad V is the transpose of L. Yeah. So, in the first equation there is a transpose missing. When I upload the notes, I will add it. Right. So, that definition is L is grad V transpose. Okay. So, we've defined L. What we need to do is develop an understanding of what it really means, and also like we did with F, we would want to remove the rotation components from it, because the rotation components are not going to contribute to the viscous stresses, right. So, the first step, let us quickly look at what its relationship to the deformation gradient tensor is, right. Because in both cases there is a deformation or a change in the shape of the material that has happened, except here we are also interested in the rate of the change of shape, right. So, if you take f and take a time derivative of it, somewhere you should be able to relate f to our velocity gradient tensor. That is what we are trying to achieve here. Again, this is one of those derivations which help you understand, but it is not expected that you will be able to do these derivations on the fly. So, if you see here, we start with the definition of f, which was dx is equal to f dot dx dash, right, and take a derivative with respect to time on both sides, right. So, dx derivative over time is nothing but the velocity vector. On the right hand side, because you have two terms, you can apply the product rule. So, you have df dt dot dx plus f dot derivative of dx dt, dx dash dt. Now, dx dash is like an initial condition here. It happened, it was what we started with, it was a fixed thing, it is not a function of the current time. So, that derivative is basically 0, right. So, you just left with one term, that dv, which was a change in velocity, is the time derivative of f dotted with dx dash. But we also know by definition of the velocity gradient tensor that dv is equal to L dot dx, that is how we have defined the velocity gradient tensor. So, this tells you that if we substitute dx using f dot dx dash, we can directly write that L dot f is equal to df dt. Yeah? Those are the two terms which we will make equal here. Yeah? Is that clear? So, what we have done is taken we have taken we are equating these two. So, L dot dx is coming from the definition of the velocity gradient tensor, and this is what we have just derived. Now, further dx can be written as f dot dx dash, what we defined f using. So, now we equate these two, right. Dx dash is the same. So, therefore, df dt becomes equal to L dot f. Okay, that is what we have written on the right hand side. And now you can take the limit that as x dash tends to x, in the sense that the deformation is really small. In really small deformations, basically f, which is your deformation gradient tensor, would be just 1, right. And so, in that limit we can say that df dt is nothing but L, and it sort of makes sense. The rate at which you are deforming should somewhere give you the velocity gradient tensor, right. The rate at which the deformation gradient is changing should give you the velocity gradient tensor, right. So, there is a derivative in space followed by a derivative in time happening in both those scenarios. Okay. So, let us talk about one example. We took the case of uniaxial extension. So, we will take a similar kind of a flow example here, which is an extensional flow. Okay. I have written a velocity field there. So, we have taken a 2-dimensional velocity field. Why? Because it's easy to represent on our 2D screen here, right. But it does not have to be a 2D dimensional field, it could be a 3-dimensional one as well, right. So, what we will try to do is we will try to depict this flow field and then derive the velocity gradient tensor for this. Okay. While we are waiting, you can try putting numbers here and seeing what you get as the velocity field. So, the velocity field V, which would have been a function of x1, x2, x3 position in space, this is just an arbitrary field that we are taking, x1 hat minus x2 hat, right. I have taken it to be independent of x3, there is no x3 on the right hand side. Yeah. So, what this allows me to do is at every point x1, x2, I can find out what the velocity vector is. So, for example, we take different values of x1 and x2. So, let us say x1 is 0 and x2 is 1, then the V1 component, which is the component in direction 1, is 0 because it is x1 hat. V2 component, which is this, would be minus 1, that is minus x2 hat, right. So, my net velocity is minus x2 hat. Yeah. Similarly, if we take 1 comma 0, V1 would be 1, V2 would be 0. So, my net velocity vector is x1 hat. Yeah. We simultaneously we can try to depict it on the graph. So this is x1, x2. So let's say this is 1, 2, 3, minus 1, minus 2, minus 3. And similarly, so 0, 1 would be here, and the velocity here is in the negative 2 direction with a unit of 1. So I can draw it like this. Yeah. At point 1, 0, which is on the x axis, the velocity is unit magnitude in the x direction. So at this point, velocity is outward here. And we can then build it further. So let's say if this was minus 1, 0, then this would be minus 1, 0, minus x1 hat. So velocity here would be and then work it further. Here you will get velocity here and so on and so forth. And you can build this entire space. So we could also take a point here. Let's say 1, 1. 1, 1 would give us 1 x1 hat and minus x2 hat, right. So one component in the positive direction and one component in the negative direction. So the net velocity component is going to be like this. Right. Are there any questions? Ah. The origin point you're saying. Yeah. L is just gradient of velocity. You have just two terms in velocity. So of course, all three, all the third row and the third columns are all 0. And so because V3 component is 0 and there is no change in z direction or the 3 direction. So what are these 4 terms? What is 1, 1? What is L 1, 1? 1 L 1, 1 is the derivative of V1 with respect to x1, right. V1 is this, and as you rightly said, you take a derivative with respect to x1, you are just going to get 1. So L 1, 1 is 1. What about L 1, 2? It is 0 because V1 is not a function of x2. L 2, 1, 0, and this is minus 1, right. So that is a simple velocity gradient tensor. Just like for the uniaxial extension case, this is also an extensional flow and you are only getting the diagonal components. Another thing that you are seeing here is that the trace of the matrix here is 0, right. And what does the trace depict? The trace is dou V1 dou x1 dou V2 dou x2 plus dou V3 dou x3, and you are getting that the sum of all these 3 is 0. What does that remind you of? Sorry? Okay, so I have heard divergence, I have heard continuity. What else? Incompressible flows. Right. So this of course is the divergence, which is nothing, divergence of velocity, which is del dot V, and what we are getting is that del dot V is 0. Yeah. This is reminiscent of incompressible flow because it tells you that when density is constant, the mass coming in, the mass going out has to be equal, and this is a relationship that is a direct consequence of conservation of mass for incompressible flows. Okay. So, therefore, this is almost always true whenever density is constant. If density is not constant, there is a slightly different form of this equation. Yeah. So, divergence also tells you what is the net inflow of a certain quantity. Yeah. That is what you are getting here. Okay. We are out of time for today. So, the correlation with the stress tensor is something we will do in the next class. Experiment of atomization of sheets, right? It's a perfect example of that. So, they have two liquid streams coming and they impinge right at one point, and when they impinge it creates a sheet of liquid, right. So, it's exactly that. So, fluid comes in, creates a sheet of liquid and the sheet goes outward. So, that's the exact flow you will generate. Okay, so we'll stop here for today. Thank you.